In this video, we're going to introduce the concept of event-driven programming. Now, we've already seen event-driven programming when we were dealing with our encoders with our Arduinos. We discovered that it wasn't a good idea to just read the encoders every 5 milliseconds, 10 milliseconds, or whatever period you wanted. But it was useful to find a way to only read them or only process them when a change happened. So only when one of the encoders went from low to high or high to low would we go and do the processing that was needed to figure out which direction our wheel was turning for our encoders. Now, the reason for this is evident if we just look at the very basic of programs. The equivalent of a Hello World program for the Arduino, which is to make an LED blink. This is probably the first Arduino code that you ever used or ever wrote, and basically it turns an LED on and off every second. Assuming that the LED is connected to pin number 9, we turn the LED on, we wait for a second, we turn the LED off, and we wait for another second again. Now, that's fine for making sure that our Arduino isn't broken, but if we wanted to do something else with this program or make a more complex program, this kind of a model would be completely insufficient. Basically, that's because if all we do is delay for a second, we can't really do anything else during that second. We're just using up processor time without doing anything useful. Alternatively, you could have a program that did something like this, which is when you push a button down, the LED lights, and when you let up the button, the LED turns off, and the program makes a beep. So we've assumed that our LED is connected to pin 9. We continuously loop through this code here, and if the button is pressed down, we loop through this while loop, and basically we set the LED pin high every time we pass through the while loop, and we set some boolean to true, boolean for the beep to true. When we let up the button, we leave the while loop, we turn the LED off, and we make a beep. And we haven't defined what make beep actually does, but we can assume that it does some kind of beep. And then the program resumes its normal loop through the main loop. Now, it's true that we could do something outside of this while loop. So whenever the button is up, it's true that we could do something interesting in this section of the code here. But while the button is down, we're basically stuck in this while loop, and we can't do anything else while we're waiting for the button to come up. So both of these codes suffer from the same flaw, which is that they are blocking codes. The delay blocks execution of other useful programs. The while loop blocks the execution of other statements that may be necessary to make a well-functioning program. So this is bad in general, and to get around this, we have to write our program in a non-blocking fashion, and one way we can do that is by using event-driven programming. Now, event-driven programming is characterized by events and services. An event is something that happens at a distinct point in time, and it's generally a change in state. So a button has been pressed, or a timer has expired. And when one of these events occurs, then control is passed to a service or a handler that takes care of whatever needs to be done when this particular event happens. So the first thing we need is something to actually check if an event has occurred. And that is known as an event checker. And event checkers are written such that we can check them frequently, and basically they're very fast. They don't occupy much of the processor time while we're actually checking for the particular event. So here's one way, for example, to check for a button press that might be relevant to the previous example. In our event checker, we've defined two different variables. One is the last button state, and one is the current button state, here just called simply button state. Now notice that last button state is declared as static, which means that even though it only has local scope, it's actually persistent. So the program remembers last button state every time we loop through the main loop and every time we come into this check for button press function. So basically, we have a last button state, we check with the current button state, and if they are different, then we are going to return true from this checker. And if they're not different, if they're the same, we'll check false. And then the last thing we'll do is we'll update the last button state based on the current button state, so that the next time we come through this loop, we'll have the correct value for the last button state. Now there are two important things to note here. The first is that we are checking for events. Event is when a change occurs. We're not just checking for the state of the system. So for example, we're not just checking if the button is down and returning true whenever the button is down. We're only